what's not missing, I've not added it right now. So because I just want you to focus on gaining experience with applying it for BFS, and syntax is going to be very similar. Probably after the contest, I'm going to be releasing the Dijkstra class in this particular as well, right? So this is graphics documentation. You can always come here and check out. So this is what it is. And how do you integrate into your code? It's going to be very, very simple, right? Here you can see the red box, graphics library code. Click on this link. It will take you to my GitHub page. And here it is saying that, hey, just copy this entire code. Here is very complicated looking things, but right from here where it shows black box start, you can just copy it all the way till here. You can copy and paste all the 170 lines. And what you can do is just paste it above the main function. So I'll give you an example. Although there are sample programs already there in the documentation, I'm still going to help you explain it. Just simply copy. Okay, this is Java. Let's go for C++. So just copy this entire thing end to end as it is. And then after you've copied it, just paste it here, right? Here is the part where you should be pasting right above the main function. Paste is as it is. And then you can start using your graphics code here, right? Like you can start doing something like graph G of 66, right? So now you can do all sorts of things that we were talking about. Then you can do graph dot add edge and all of those things, right? So this is the place where you want to paste it just above the main function. That is it, because it's a simple library. You don't need to install. You don't need to do anything. You can just copy paste it anywhere on any platform and you should be good to go. So again, I'm going to be pasting the link for that. So do not be worried if it is not opening for you. That's perfectly fine. And this is the GitHub where you can copy it. And again, this is my library. So if you want to bookmark it, you can also star it. This is my library where I've implemented all kinds of algorithms for ICPC or all of those things. It has all advanced algorithms and all of those things like that, right? So you can go to this algorithms notebook that I have. Yes, PHP Duke is my Codeforces handle, if you can guess by now. So you can come here and you can bookmark it in order to, you can star mark it in order to, keep it handy for your reference. So this was the graphics library for you. This is all that we needed to know. And with this, you will get started to implement, convert your ideas into code really, really fast. Instead of taking a lot of time, you'll be able to kickstart it very, very fast. However, for interviews, try to always this is going to help you to start converting your ideas into code very fast. But later on for interviews, for example, you should know how to implement BFS from scratch, right? That's going to be helpful where you cannot copy paste the code like in the setting of interview. But for the sake of this particular week, till the contest we are going to be doing, it is perfectly okay to use this library in order to focus all into problem solving. Trust me, even though implementation sounds complicated or it looks daunting or any of those things, it's very easy to learn, right? It's in fact the easiest part to learn in any kind of data structures of algorithm, right? Amrita, you can copy paste this library in the contest that we'll be having, and you can simply start building graph, and you can just start building the graph and voila, you're done. That's all that you need to be doing, right? So this is all about graphics library. Now we are going to start solving some of the basic, very easy, but classical and important problem categories, right? That you should be knowing in order to actually know how to use this graphics library, right? So I'm going to go for some basic problems. So right from 2000, I think 10 or something like that, from that point of time, there is a very common pattern where a graph problem is given to you as grid, right? So this is the most common pattern. So you should be knowing how to solve this problem, how to implement this problem. Yes, Rana Suryam, the contest that we will conduct will completely be based on all the things that we have learned. which is graph itself, right? Rishikesh Weber, I hear you. You want me to extend graphics for Java. Like I'll try my best to also extend it to Java as soon as possible. All right. By the way, how many people are using Java? Just comment out Java on the chat. Just Java on the chat. That would also help me understand how many people are there who are using. Okay, all right. I can see 40, 50. Okay, 50 people are almost using Java. Okay, people are still commenting. Fatafat said, don't keep me waiting. Continue, commenting. Okay, so almost 70 people, okay, people are still messaging. Okay, wow, that's quite a lot. Almost 110 people have voted that they are using Java. Okay, let's do similar vote for Python. Okay, Vivek, putting out so many messages is not going to help anybody. So put out Python, on the chat if you are using Python. That would also help me understand how many Python users do we have. All right, understood. So almost we have 70 people in Python as well. So out of 2000 people who are attending this graph camp, I can see almost 110 people on Java and um, okay, 70, 80 people for, let's say 80 for Python as well. So almost 200 people are non C++ users. So no problem. I hear you. I'll try my best to also extend it to Java and Python as soon as possible. We'll keep you posted about it. All right, perfect. Sure, Anjali, I'll try my best to do that. So now we are moving to the language agnostic and problem solving part. Again, as I've discussed, today is going to be the easiest day, but these are classical and important problems so that you know how to solve them. So very basic example of graph as a grid is like, let's say you're given a grid like this, right? And every single cell will have either it can be empty or it can have a wall on it, right? So for example, let's say if we have a wall on a particular cell, it is going to be marked as X. So let's say this is how the cell this is how the walls are, and you'll be having a starting point and you want a target where you want to reach, and in a single step you can either move top, down, left or right. So the question is, what is the minimum number of steps so that you can go from S to T? So if anybody can quickly tell me what will be the answer for this particular sample, that would be nice. Okay, Anvish, you don't need anything like 01 BFS. Those are all very simple ideas, but people love to give name, so they have overcomplicated those things. Again, this is going to be a simple BFS. We are going to see very, very soon how. Okay, so a lot of people are saying 7. A lot of people are also saying 6. So let me verify which of the lot is actually correct. So in the first step, I will go from here to here. Second step here to here. Third, okay, third, and then fourth, then fifth, then sixth, and finally in seventh, I am going to be ending up at the cell with T, right? Which is my target location. So answer for this particular sample is 7, right? So how can we solve this? Of course, this smells like shortest path problem. Yes, Bharadwaj, this is like a maze that is given to you in the problem. How can you solve it? No, you cannot. It is going to be very difficult to solve it using dynamic programming. But with BFS, it is going to be straight and simple. Okay, Anurag is saying a similar question came in the last ad code round. Okay, that's interesting to note. Anurag, thanks for letting all of us know. Yes, so Anurag is right. What we can do is we can start seeing this grid as a graph, right? So there are 4x4 size grid. So we can make 4x4 different kinds of nodes like this. All right. So this is how you can do it. And now how can you label this? Probably you can label it something like this. You can label it like 1, 1, 1, 2, 1, 3, 1, 4. 2 comma 1, 3 comma 1, 4 comma 1, 2 comma 2, 2 comma 3. You get the idea, right? 4 comma 4. So this way you can actually convert every single cell into a corresponding node. And now how do you add edges? What you can simply do is go to each cell and figure out what is the cell on right of it, below it, above it, and left of it. If there is no cell, or if there is a cell with X, then do not create edge, otherwise create a edge. So for example, corresponding edges is going to look like this. Can I create an edge like this from 1 1 to 1 comma 2? No, because in the original graph here you have a X, so you cannot travel to this particular node. So what your graph is going to look something like this, right? Let me quickly draw it for you. So this is how your graph is going to look like for this particular sample. Okay, my bad. There is no edge here as well because that is also X. Thank you for pointing that out. Vivek and Abhinandan, you are very, very sharp. So yes, this is how it is going to look like. And now once we have this graph, now it's a very simple problem. Here is the source node. Here is the target node. You can simply pass this graph to BFS with source node as source, find the shortest distance to target, and that is your answer. You can simply do yes, Pulkit is already has already got the flavor of GraphX. He's saying bfs.run, and then he's already talking in that context. So that is right. You can simply use GraphX to build a graph like this. Whatever is a n plus whatever is number of nodes, you can just simply do a size of graph, and this is what you can do. And then you can continue adding edges like this in order to this is a very cool part. If you notice, the edges are now two-dimensional. It's no longer labeled as 1 2 3 4. It is labeled as 1 comma 1, 1 comma 2, 1 comma 3, and things like that. So how can we manage adding two-dimensional graphs? What we can do is, you don't even need to use pairs or anything like that, right? What you can simply do is, you can simply write 1 comma 1 comma 2 comma 1. So this is all. Instead of writing here 1 comma 2 in order to create edge from 1 to node 2, here in two-dimensional graph you just need to use curly braces and the syntax remains as it is, and GraphX is going to manage it out of the box for you. This will create an edge like this, right? So this is how you can GraphX becomes handy. Like, it automatically handles two-dimensional and three-dimensional graphs for you out of the box. Once you have created a graph like this, once you have added all the edges and things like that, then what you can do, all you need to do is BFS. BFS, you already know how to do it. Pass the graph to it by reference, and then do BFS dot run. And what is your source? Here it is 1 comma 1. So all you need to do is 1 comma 1, right? And that will run the BFS from here. So you basically get the picture. Two-dimensional, three-dimensional nodes you don't need to be afraid of. And as you can see in grids, it becomes so much convenient for us in order to not use 1 2 3 4. We can absolutely do that as well, or we can do something like this as well, right? So this is how you can actually implement this, and I'll leave the rest of the code for you. Again, there is a sample code for this particular problem that is also provided to you in the documentation. Okay, Vanshika is asking, don't we need to remove some of the nodes? More than removing some of the nodes, Vanshika, we are not adding corresponding edges. So instead of not having 1 comma 2 as a node, I don't care if it exists like that. It's perfectly fine. What I'm going to do is, in this particular step, when I'm constructing the graph, I'll ensure that I'll not add any edge to this particular node called as 1 comma 2. So that is how I can, Vanshika, I can do this. Rohit, link for documentation I'm going to be posting in the WhatsApp. So do not be worried about that. So this is our problem 1, down and dusted. This is very simple, but classical form of problem that everybody should know, because from 2010 itself, this has this idea of using problems of grid and then posing a graph problem is very, very common. right? All right, so this was the problem number one. Let's go to another classical, basic, but again useful and important problem, which is called as finding number of components. This is important problem for different kinds of reason. Whenever you think about graph, you almost think naturally as a single connected component, and that is a mistake. Let me give you an example. A single graph could look something like this, right? Let's say A, B, C, and let's say D and E, and then let's say F, something like this. So even this entirety is also can be considered or given as a single graph. So this is one single graph G, and this single graph G has multiple connected components, right? A connected component is where you can travel from one node to every other node in that particular component. So clearly you can this is the first component, this is the second connected component, and this is the third connected component. So this is a single graph G which has three connected components, right? So this is what it means. So problem statement is fairly simple. Given a single graph, find number of connected components in this graph. So this is also a fairly classical problem. I'm going to show you how can you solve this problem. So that will also help you learn how to use GraphX. So what we can do is we can devise a very simple algorithm. What we can do is we can go to every single node and find out have we already explored this particular component or not. If this is a new component, we do answer plus plus, and then we explore the entire component. And if you've already visited this particular component, then we are going to not do anything, right? So that is exactly what we have to do. Yes, Aditya has got it right. We'll have to do multiple BFS. So let's start one by one through every single node. So we go first for the A. Initially, we have not visited anything. So that is everything is going to be unvisited. As soon as I go to A, I'm going to find that, okay, I have never visited. In the BFS class, you can find that out by is underscore visited, right? That is what you can go and check. So I'll also write the pseudocode for each node. What we are going to be doing, we are going to check if BFS dot is visited. This is also a function that is provided of the current node. If that is equals to false, that means we are encountering a new node where we have not explored the component. So as soon as we find a new component, of course, we first want to do answer plus plus. Then we would want to explore the entire component. The way we can do is by running another BFS with source node as this particular node itself. What this will do is it will visit all the possible nodes I can visit from current node, and that is going to mark them as visited, and it is going to compute its shortest distance. So this is the simple, fair enough, simple code. We go to A and then we check if A is visited or not. Obviously in the beginning, all of them are not visited. So we'll go and we'll increment the answer from 0. Answer will become 1. And then we are going to do BFS from this particular source node. And what this BFS is going to do, it is going to compute shortest distance from A to every other node. This is going to be 0. This is going to be 1. This is going to be 2. What about D, F, and E? Because you cannot travel to those nodes, those will not be computed. Everything will stay default, which is infinite distance. So all of these will stay as infinite, just like that. So what we have done is, if you see, we have using BFS, we have explored the entire single component, and now we have explored the entire single component. So the next time, once we have visited A, then we go to B. B already has a distance because we have already visited it during the last BFS. So BFS dot is visited is actually going to be true. And because we have visited node B in the prior BFS, so we are going to do nothing. Similarly, we go to C and we'll again do nothing because again we have the edge weight for it. So it is already visited during the first BFS. So we'll do nothing right now. What will be interesting is when we are exploring node D, Then again, we have never exploded because distance to it is infinite. So is visited will show out to be false, and we'll do the answer plus plus in order to mark that we have now just discovered a new component, right? As soon as we do answer plus plus, our answer becomes 2. And now we'll again explore the entire component where node D exists. So we do a BFS from node D, and now here we are doing BFS. So of course it is going to be marking as 0 and 1. And again, it will not mark anything to E, or it will not even affect distances in the component, in the first component. So this entire component is also visited. We have already counted that, and we have already visited D. Next, we go to F. Again, we have already visited this, so we'll do nothing because is visited will return true. Finally, we come to the last component, which is E. Because it is unvisited, again, we are going to do answer plus plus. This becomes 3. We have now we'll do BFS, and in BFS, the only way that's going to be changed is going to be this. And now we have successfully run every single thing. And at the end of the answer of this loop, you can simply print answer, right? And that will turn out to be 3, which is the expected number of correct components. Simple, straight, but still very, very effective, right? So let me quickly do a poll and see if people have understood both the two problems or not. All right. Thank you, Siddharth. Happy to see that you're finding the explanation simple and easy to follow. All right, so quickly vote out yes if you've understood the problem and the solution, both the solutions, number of component, and the graph as a grid. And if you've understood both of this, then that should be great. All right, Manoj, bfs.run is going to be simply going to be like, it will start a BFS with the source node. You can provide it in bfs.run, right? So super quick recap, whatever we have done, I'm going to do that. What we have done is we have learned GraphX library. Just like we declare integer A, just like that, we can declare our custom class type like car, BMW. And just like data type here, integer, same in the same fashion, car is that data type. And just like A is the object variable where you can assign values and stuff, here BMW is that variable or the object type, right? Yes, Parth, you should be able to implement every single kind of problem using this library, which are related to BFS, of course, right? So we learned this, and then we learned GraphX currently has 2 classes, graph and BFS. And we also saw a sample code on how to declare, how to build a graph, how to add edges, how to do BFS. BFS, you have to supply always a graph when you're initializing it. And then you can do bfs.run by providing the source node, and it will do BFS on graph G with whatever source node that you have provided. This will take O of nodes plus edges time complexity. And every single time, you do bfs.min distance from 5, it will find you the shortest distance from 3 to 5, and this will be constant time, right? So this is how we can use this. Then we saw graph as grid, that hey, we can simply start seeing grids as graph, and you can imagine it as 2-dimensional graph, and you should be able to simply use GraphX library as it is. By the way, if you know how to implement BFS from scratch, I think that is going to be shorter to code and it is going to be much easier. So if you know that, great. If you do not know that, you can later on learn, which I suggest you to learn later on after this week and the camp has ended, to learn BFS from scratch all by your own, right? So उसके आपको बहुत content मिल जाएंगे internet पे. Those are very trivial stuff, simple and easy to follow and learn, right? And then we saw problem number 2, which was about number of components. And we saw that, hey, we can use BFS multiple times in order to solve this problem, right? And this is how we can solve this problem. I've also given you a short, sweet, simple pseudocode. Exact code also will be provided in the documentation. So with this is all that I wanted to cover regarding implementation. This will help you. I hope GraphX will help you, which is the main goal of it, to convert ideas into working codes that you can submit on any online judge, LeetCode, Codeforces, or the job workflow where I'm going to be giving you assignment into working code. That is the main purpose of it, so that you can just focus on problem solving and use this library to convert ideas into working correct implementation codes. That's the beauty of it. That will make the process extremely fast. You can code any kind of problem in under 10 or 15 minutes. You can implement it probably in 5 minutes, 7 minutes, but just